Now, another method to minimizing, maximizing, finding these extreme values based on, like we had there, a constraint. The volume was constrained there, is to use the method of what's called Lagrange multipliers. Now, the way this works is, let me set up a scenario here, okay? So let's say we've got an f of xy. So we want to find the extreme values of some two-variable function is equals f of xy, whatever. And we want to make that subject to this constraint another two-variable function, say, is equal to some constant. Very similar to, like the volume problem. Find the minimum surface area if the volume is equal to this certain value. Okay? Well, to kind of give you the picture here, what we can do is look at some level curves for this, just to kind of give you the idea. Let's look at level curves for our, and this is just our hypothetical here. In other words, we're just going to make this up, but let's say our level curves come in looking like this. Like, for example, if f of x of y equals 1, then let's say our function values, our level curve looks like that. Just a hypothetical here. And let's say it does kind of grow. Let's say f of x y equals 2 is this. And then f of x y equals 3, this, 4 here, okay? So you can kind of see kind of a logarithmic kind of curve, I guess, but just hypothetical. It could be whatever. All right, well, we want to find the largest of these values such that g of x y equals k. And so what I need to do here is map out our, plot out our, this function, right? G of x y equals k. And let's just happen to say g of x y equals k does this. So the question is there an extreme value we can determine based upon that? So this is g of x y equals k. Right here. So is there anything we can say about, so basically what this says is I need an x comma y, or I need to find the extreme value at a particular x comma y for f that also satisfies this function. Is there anything you can see about that? Where they meet, okay? All the times they intersect, okay? So if you look at this value, we've got some where they intersect, and so those would be, and of course, with other level curves like 2.5, we'd have some. But where is the maximum as far as f is concerned? Right here. This right here is the maximum f value. Now, that's where they intersect, but what even more could we say about where those occur? Don't they have the same tangent lines?
Yeah.
Same tangent lines. The maximum is where they have the same tangent lines, because up here, the tangent line for G is different than the tangent line for F. Same thing here. Okay, and at any other, I mean, we didn't do the like 2.5. You got a 2.5 value, but same thing there. The maximum is for F, because even if we looked at this one, the F value is 2. Here the F value is 1, right? Here is the maximum F value we get out of that. Okay? So the maximum F value there is occurring where F and G have the same tangent lines. Now, to relate that to some other stuff then, that also means what about the normal lines? The normal lines would be parallel, or the normal. So the normal lines would be parallel here, you know, because the tangent lines are the same. We'd have the same normal direction for your normal. So we could say that the normal lines are also parallel, which means that the gradient vectors are parallel, right? Because that's what the gradient vector here tells us about. So could be, I mean, depending upon, well, the normal vectors, okay? That's what we're talking about. We're talking about, because when we talk about gradient, the normal lines, yeah. So the gradient vectors are parallel. You know, vectors can change size. So in other words, the gradient of F equals, at that particular x, this is x naught, y naught, equals some, and this is, we're going to use the Greek letter lambda, some constant times the gradient vector of G at x naught, y naught. This is where the x naught, y naught we're talking about. So yes, this is called, like I said, this is the Greek letter lambda. That's called the Lagrange multiplier. You can't say that about any other point on this. Right now, I'm going to draw some others here in a second. But you can't say that about any other point there. But you can say it about that point, because that's where your tangent lines are the same, so therefore your normal lines are the same, which means your gradient vectors are parallel. Okay? Now, notice also, if we wanted to, let's say our g of xy continued on out here, just kind of connected up, kind of an elliptical shape. Well, if we continue our level curves, they kind of seem like they're doing this. So let's say that's f of xy equals 0, f of xy equals -1, f of xy equals -2. So where would you say the minimum f value, what's the minimum f value here? So our maximum f value is 3. About -1.5, okay. Approximately -1.5. Yeah, it's going to occur somewhere between -1 and -2 because that's where our tangent for our level curve is going to come in, somewhere like that, we're guessing. Just following the pattern there. Yeah, so the minimum, so we can do the same thing for the minimum value, where the tangent, where these two tangentially hit. If that's a word or not, but okay. All right. And so again, at that point, the gradient of f would have to be some multiple of the gradient of g, because they're tangent lines are the same, so their normal lines would be the same, and the gradient vectors would have to be parallel. Okay. All right? Okay. Now, same thing is true for this also holds for 3 variable functions, and I think that's the way that the book lists it here. To find, so this is, they call this the method of Lagrange multipliers. Or multiplier. To find the max min values of f of x, y, z subject to a constraint g of xy equals k. Find all values of x, y, z, and sometimes this lambda. Sometimes you don't have to find lambda, but find the values of x, y, z, and lambda, because really we're looking for the max min values of this, so all you really need is x, y, and z, but sometimes you do have to to solve lambda. Find all values of z such that the gradient of f equals lambda times the gradient of g, and gxyz equals k. There is one note here. For this to work, the gradient of g cannot equal 0. If you've got something where the gradient of g equals a 0 vector, going to have a slight problem. Yeah. Right. Yeah, it would not exist. Right. Okay. Now, basically what this then means is that if you've got this, your gradient of f is f of x, partial with respect to x, partial with respect to y, partial with respect to z, right? That's our gradient vector for f. The gradient vector of g is partial with respect to g, partial with respect to x, partial with respect to y, and partial with respect to z. And so this amounts to 3 equations, doesn't it? 3. if the gradient equals lambda, so what this means is really three equations, right? This means that the partial of f with respect to x must equal lambda times the partial of g with respect to x. And it also means that, you know, if these vectors are like this, the partial of f with respect to y must equal lambda times gy. Partial of g with respect to y, and the partial of z is lambda times partial of g with respect to z. So really, what this method amounts to is that we've got four equations, these three and this one, and four unknowns. Because this is an x, y, z equation, so all these are going to be in x, y, and z. And so is this one, because that's just a number. Okay? All right. So solving, to find the max min values, you're solving a system of four equations for unknowns, which can be sometimes a little tricky, but you have to use. Okay.